Have you ever wondered why the current in transmission lines tends to flow more towards the outer surface at higher frequencies? Perhaps you've noticed this phenomenon and pondered its implications. For those in the field of electrical engineering, it's an essential concept that can't be overlooked. This intriguing behavior of current is not a random occurrence, but is governed by a principle known as the skin effect. And it plays a crucial role in the design of transmission lines. So let's delve into this fascinating world of the skin effect. The skin effect might sound complicated, but it's a simple concept at its core. Picture a current flowing through a conductor, like water flowing through a pipe. Now, if the water represents an alternating current, or AC, then the pipe is our conductor. In an ideal world, this current would flow uniformly across the entire cross-section of the conductor. But we live in a real world where some interesting phenomena occur. One such phenomenon is the skin effect. The skin effect is the tendency of alternating current to flow near the outer surface of the conductor, like water preferring to flow near the edges of a pipe. Why does this happen? Well, it's all about the changing magnetic field induced by the alternating current. This changing magnetic field restricts the flow of electrons, pushing them towards the outer regions of the conductor. Now picture a crowd of people in a hallway. If everyone tried to move through the hallway at the same time, it would get congested, right? Similarly, when more electrons are pushed towards the outer regions of the conductor, it results in a higher current density near the surface. This phenomenon becomes more pronounced as the frequency of the AC signal increases. Think of it like a crowd of people moving faster and faster through the hallway. The faster they move, the more they tend to stick to the edges to avoid collision. So, what does this mean for our conductor? Well, because the current is concentrated near the surface, the effective cross-sectional area for the current to flow decreases. This is like narrowing the hallway for our crowd of people. The result is an increase in the resistance of the conductor. As a consequence, this uneven distribution of current and increased resistance lead to higher power losses in the form of heat and reduce the overall efficiency of the transmission system. So the skin effect results in an uneven distribution of current and increased resistance in the conductor. Now you might be wondering, how does this skin effect impact transmission lines? Well, let's delve into that. Imagine a bustling highway with cars zooming past. Now what if I told you that due to a peculiar phenomenon, most cars preferred to drive on the outer lanes rather than evenly across all available lanes? That's essentially what the skin effect does to the current in transmission lines. The skin effect is like an invisible force field that nudges the alternating current, AC, to flow near the outer surface of a conductor, rather than uniformly across the entire cross-section. It's like the current is shy of the conductor's core and prefers to stay near the skin, hence the name skin effect. As the frequency of the AC signal increases, this shyness becomes more pronounced. The current density becomes higher near the outer surface of the conductor. It's like the higher the frequency, the stronger the force field that restricts the flow of electrons to the outer regions of the conductor. Now, this might seem like an odd quirk of physics, but it has very real implications for power transmission lines where AC is commonly used. This uneven distribution of current effectively increases the resistance of the conductor. It's like forcing all the cars to use fewer lanes, leading to congestion and slower traffic. This increased resistance, in turn, leads to higher power losses, much like how a traffic jam leads to wasted fuel. It reduces the overall efficiency of the transmission system, like a highway that could carry more cars if only they'd use all lanes. This is why engineers need to be like savvy city planners when designing transmission lines. They have to take into account this peculiar preference of AC for the outer lanes and come up with strategies to mitigate its impact. Some of these techniques include using hollow conductors or employing multiple smaller conductors in a bundle, much like creating additional outer lanes or multiple smaller highways. Therefore, engineers need to consider the skin effect when designing transmission lines. By understanding and mitigating this phenomenon, they can design more efficient transmission systems and keep the current flowing smoothly, just like a well-managed highway. Let's delve into the disadvantages of the skin effect. The skin effect, while an inherent aspect of AC transmission, isn't without its downsides. The first major disadvantage is increased resistance. As the skin effect forces the current to flow more towards the surface of the conductor, the effective cross-sectional area carrying the current decreases. This leads to higher resistance, which in turn results in increased power losses in the form of heat. This brings us to the second downside: energy losses. The higher the resistance, the more energy is lost as heat. In power transmission lines where efficiency is paramount, these increased energy losses can significantly impact the overall efficiency of the system. The skin effect also presents limitations at higher frequencies. It becomes more pronounced as the frequency increases, affecting high-frequency applications, such as radio frequency transmission. This can limit the effective use of the conductor and might require special design considerations to minimize its impact. Next, we have complex design requirements. To mitigate the skin effect, engineers designing transmission lines need to take it into consideration and implement design solutions. These can range from using hollow conductors to employing multiple smaller conductors in a bundle. However, these solutions add complexity to the design process, leading to increased costs and challenges in practical implementations. Lastly, there's the issue of uneven current distribution. The skin effect causes the current to be concentrated near the surface of the conductor, leading to an uneven distribution of current across the cross-section. This non-uniform distribution can lead to issues such as increased electromagnetic interference. In conclusion, while the skin effect is a natural phenomenon in AC transmission lines, its disadvantages, including increased resistance and energy losses, necessitate careful consideration. Engineers and designers must employ smart design strategies to minimize the skin effect's impact on the efficiency and performance of the transmission system. These disadvantages necessitate careful consideration and design strategies to minimize the skin effect's impact. So how can we reduce the impact of the skin effect in transmission lines? Well, let's delve into some of the methods commonly used to mitigate this phenomenon. First up is the use of Litz wire. Short for Litzendraht, Litz wire is a type of conductor that consists of multiple individually insulated strands. With each strand carrying a portion of the total current, the combination of these strands helps to distribute the current more evenly across the conductor's cross-section. Now that's a smart way of outsmarting the skin effect, isn't it? Next, we have the strategy of employing multiple smaller conductors in a bundle. By doing this, we effectively increase the surface area for the current to flow. This method helps to reduce the overall resistance and minimize the skin effect, ensuring a more balanced distribution of current across the conductor. Think of it as a team effort, where each small conductor contributes to the overall performance of the transmission line. Last but not least, there's the option of using hollow conductors. Now you might be thinking, why would we want to do that? Well, since the skin effect causes the current to flow more near the surface of the conductor, the central part of a solid conductor doesn't contribute much to current conduction at high frequencies. So using a hollow conductor can provide the same performance while saving on material costs. It's a win-win. These techniques, while seemingly simple, can significantly improve the efficiency and performance of transmission lines. By mitigating the skin effect, we're not only reducing energy losses, but also maximizing the potential of our transmission systems. It's all about making the most out of what we have and ensuring that every electron does its part in the grand scheme of things. So, the next time you come across a transmission line, remember the clever tricks engineers use to combat the skin effect. These techniques can help to improve the efficiency and performance of transmission lines. To sum up, the skin effect is a fascinating and important phenomenon in electrical engineering. It's the tendency of alternating current, or AC, to flow near the outer surface of a conductor, rather than uniformly across the entire cross-section. As the frequency of the AC signal increases, the current density becomes higher near the outer surface. This, in turn, leads to an uneven distribution of current and an effective increase in the resistance of the conductor, resulting in higher power losses and reducing the overall efficiency of the transmission system. This phenomenon poses challenges in the field of electrical engineering, particularly in the design of power transmission lines. It's responsible for increased resistance, energy losses, and limitations at higher frequencies, all of which can hamper the performance and efficiency of the transmission system. Nevertheless, engineers have devised methods to mitigate the skin effect. One such method is the use of Litz wire, a type of conductor made up of multiple individually insulated strands. Each strand carries a portion of the total current, helping to distribute it more evenly across the conductor's cross-section. So, you see, understanding the skin effect is much more than a theoretical exercise. It's a practical necessity for anyone involved in the design and operation of electrical transmission systems. And that brings our deep dive into the skin effect to a close. Understanding the skin effect is crucial for designing efficient and effective transmission systems. Thanks for watching, and stay tuned for more interesting insights into the world of electrical engineering.